Alright, so I'm Cameron,
I'm Luke.
and we're going to talk about how we created our planet from the very beginning. So the first step that we took in the process was we created the stars in the system. It's a binary star system, and Luke can give you some of the information on that.
So a binary star system is made up of two stars. The primary star we named Kerbal, and the secondary star Kerbil. Kerbal has a mass of 1.25 SOL,
Solar masses.
solar masses, a luminosity of 2.44 solar masses, the density is 1.18 solar masses, the temperature is 1.23 solar masses, the distance to the barycenter.
Yeah, the barycenter is the center of a binary system, and it's the imaginary point where two binary objects orbit around.
That distance is 0.11 astronomical units. The eccentricity is 0.4. The max distance to the barycenter is 0.224 astronomical units. And the minimum distance to that barycenter is 0.096 astronomical units. The second star has a mass of 0.5 solar masses. The luminosity is 0.0625 solar masses. The density is 0.6 solar masses. The temperature is 0.7 solar masses. The distance to the barycenter is 0.05 astronomical units. The eccentricity is 0.45. The max distance to the barycenter is 2.32 astronomical units, and the minimum distance to barycenter is 0.088 astronomical units. The habitable zone of this system is 1.5 astronomical units to 2.17 astronomical units. The frost line is 7.6 astronomical units. The star max separation is 0.456 astronomical units, and the minimum separation is 0.184 astronomical units. The no planet zone is 0.061 astronomical units to 1.368 astronomical units.
Planet no zone is basically so much gravitational, basically it's the point where there's so much stuff going on in the system with the two stars that nothing can orbit there. And then Patrum, which is our planet, it's actually derived from the Latin word for rock, Patram. I'm sure I butchered that.
Patram.
But it has a mass of 0.8 Earth masses and a density of 6.03 grams per centimeter cubed, which is fairly similar to Earth. It's got a radius of 0.9 Earth radii, a gravity that is 0.988 times Earth's gravity, an axial tilt of 10 degrees. It's got an average orbit of 2.05 astronomical units, an eccentricity of 0.08, and its closest distance to the Kerbal system is 1.97 astronomical units, with a max separation of 2.13 astronomical units. The Hill sphere of Patrum is 248 Earth radii, with a Roche limit of 1.54 Earth radii. And we have a moon similar to the Earth's moon, The moon has an inclination of 1 degree, so it's fairly close to the orbital plane. It has an eccentricity of 0.01, and it's got an orbit of 50 Earth radii, so it is relatively close to the planet. It has a radius of 0.37 Earth radii, and a density of 3.62 grams per centimeter cubed, with a mass of 0.033 Earth masses, and a gravity that is 0.24 times Earth's gravity. So the atmosphere of Petrum is relatively similar to Earth. It's got 63% nitrogen, 27.6% oxygen, 5.7% hydrogen sulfide, which is very different from Earth, as on Earth it is a toxic gas, but on our planet it will be used for chemosynthesis. It's got 1.5% carbon dioxide, also once again a lot higher than Earth, 1% argon, and trace amounts of other gases. The atmospheric pressure of our planet is 1.2 Earth atmospheres. Alright, and so when it came to creating the planetary features like the continents and the oceans and all like that information we need to know, like the currents and wind patterns, I used a program called G-Plates, which allowed me to draw different continents and then move them around basically however we wanted them to move, and allowed for us to simulate continental drift. So we did the current map and then the wind map, which allowed us to create this, which is the first 100 million years of our planet. Well, not the first 100 million years, but the first 100 million years of our simulation. Would you like to talk about a bit about this era, Luke?
So, this area has the average temperature of 26 degrees Celsius in the summer, a 50 degrees Celsius in winter, with wide temperature swings due to the binary star system. The summers are relatively short and cold, while
short and warm.
Short and warm, while the winters are long and cold. As you can see on the map here, compared to the wind flow, you can see the amount of desert with the separations of the mountains and some smaller islands within the middle. On the second 100 million years, we have a little bit different currents, a little bit different wind pattern because of the same wind pattern but a little different continental movement because of because the continents moved. So, Nick, you want to talk about how this era is? So as you can see, a lot of changes have happened. The continent, instead of being somewhat one whole area,
One supercontinent,
has split into two different continents. This created a more, what do you call it, like a moisturized area?
more moist area on the continent.
On the right continent, where there once was desert, due to the mountain range located on the left continent. Because of the ocean split, that area is now able to provide for trees and normal grasses and such.
A lot of jungles and wetlands will form in that new continent now.
In the north of the left continent, a lot of land has been
Has sunk.
sunken into the oceans. This creates a lot less area, obviously, up there. And the same is true for the right side, as the area grew smaller due to the split with the continent. The temperature in this second 100 million years has an average of 16 degrees Celsius in the spring and fall, 22 degrees Celsius in the summer, 11 degrees Celsius in the winter, with wide temperature swings due to the binary star system.
And in the third 100 million years, we have reached pretty much the midpoint of our little simulation. So, once again, the continents have split once again into 4 major continents instead of just 2, and it allowed for a lot more movement in the currents, and did a lot of changes to the environment. Wind patterns stayed pretty much the same. Well, they would have stayed pretty much the same. Just a quick disclaimer with the wind. Didn't go super in depth because it is extreme. The wind patterns are extremely complex, and it would have taken me years probably to accurately simulate what the wind is like. And Luke, would you like to talk a bit about this era?
Alright, so let's split into 2 once more. You can see, obviously, there are 4 more islands, with some smaller islands showing up in between the left 2. Again, nothing much has changed with the actual climate, as the wind patterns are still relatively similar, and not much has sunk into the ocean either. The temperature in this third era is 15 Celsius spring and fall, with a 21 degrees Celsius summer, 10 degrees Celsius winter, and yet again, this temperature swings due to the binary star system.
And Luke was the one that created those sections of, like, he created those those biome maps of those eras, and I was in charge of creating the biome maps for this era. So the current patterns once again have changed dramatically due to continents moving, and we thought for this one, why not throw in a little bit of a mass extinction to reset some of the ecosystems. So I decided an ice age would be pretty good. So this time the planet is a lot colder, with a lot more of a continent, and like a Antarctica like continent moving north, drop in ocean levels, resulting in a lot more deserts and a lot less rainforests. There's quite a bit more grassland and a lot more tundra and snowy area. And this era has a planetary average of 5 degrees Celsius in the spring and fall, 10 degrees Celsius in the summer, and -1 degree Celsius in the winter. So basically in the winter, lots of the oceans will freeze over, and basically all the lakes would start to freeze up. Once again, wide temperature swings due to it being a binary star system. And we are now 100 million years away from the present. Once again, there's some more current changes, and the continents have begun to recollide. So there's once again 2 supercontinents starting to form, one in the north and one in the south. So there's still a lot of snow and ice and quite a bit more mountains forming, as well as just one big ocean in the equator. So there's still a lot less rainforests. But it's a lot warmer now, with a planetary average of 10 degrees Celsius in the spring and fall, 16 degrees in the summer, 5 degrees in the winter, once again with wide temperature swings due to the binary star system. And finally, we've reached the present. There's now once again one supercontinent, and well, there's 2 continents, one supercontinent in the center of the near the equator, and then one Antarctica-like continent in the north. So there's still a lot of snow and ice, huge mountain ranges, big deserts, a lot of rainforest, and then some plains, as well as there's a lot more ocean than the past few years, as more land masses have started to sink below the ocean. And it's also warmed up a fair bit, so it is now 17 degrees Celsius in the spring and fall, 23 degrees in the summer, 11 degrees in the winter, as well as wide temperature swings due to the binary star system. And here's just a quick video of how the continents have changed from over the 500 million years. And next time we'll start to peek into how life will get its first footholds in the ocean. This was Cameron.
I'm Luke.
And see you next time.